Hello, these are the solutions to AP Physics C Mechanics suggested problem set 6.2, the minimum suggested problems, which are listed here. The first problem is about two ice skaters that are practicing. One, Daniel, has a mass of 65 kilograms and is struck by another skater, Rebecca, who is moving toward Daniel and has a mass of 45 kilograms. And she is moving at 13 meters per second. Now, it says after the collision, so this entire setup is for before the collision. After the collision, it is revealed that Rebecca is now moving at 8 meters per second. So we'll say this is V2 of Rebecca, moving at 8 meters per second at an angle of 53.1 degrees from her initial direction. So this was her initial direction, is in the horizontal direction. So we can say that really what's going on here is this is V1 of Rebecca. V1 of Daniel is equal to 0. And V1 Rebecca is completely in the x direction. Then after we collide, Rebecca is moving in one direction at 8 meters per second. And that means that Daniel is moving in the somewhat opposite direction at some different speed. So V2 of Daniel, we don't know. We also don't know what we'll call theta. So we're going to try and find the magnitude and direction of Daniel's velocity. So in order to do that, we're going to set up conservation of momentum. So I have P1 is equal to P2, and these are vector quantities. And so since I have a two-dimensional problem in the end, I need to do the x and the y's separately. So for the x direction, P1x is equal to P2x, and I can break this into mass of Rebecca times her initial velocity in the x direction, plus the mass of Daniel times his initial velocity in the x direction, is equal to the mass of Rebecca times her final velocity in the x direction, plus the same for Daniel. Now, for this particular problem, Daniel has no initial velocity, so this entire term is 0. Now, after the collision, we have enough information here to say that we know mass, we know V2 arc, it's a speed, but we don't necessarily know V2 Rx. So we need to go ahead and go back and do that. So from the information we were given, we know that V2 of Rebecca in the x direction is going to be V2R times the cosine of this angle, 53.1 degrees. And so V2 of Rebecca in the, actually let's do this. V2 of Rebecca in the x direction will be 4.8, we'll just round to 4.8 meters per second. And in the y direction, since we will probably need that later, we have V2R times the sine of this angle, 53.1 degrees. And so we would have 8 times the sine of 53.1 degrees, which is we'll just round that to 6.4 meters per second. So we have Rebecca's velocity afterward. Now we can actually use this to find the velocity of David in the x direction after the collision. So I'm going to go ahead and rearrange this and look for the velocity of David in the x direction. So V2 dx will be equal to mass of Rebecca times V1r in the x direction minus mass of Rebecca times V2r in the x direction, all over the mass of Daniel. So substituting for these quantities, I would have the mass of Rebecca, which is 45 kilograms, times her initial speed in the x direction, which is all of the initial speed, so that's 13, minus mass of Rebecca again, 45 kilograms, times her final speed in the x direction, which we found to be 4.8 meters per second. So we have 4.8 all over the mass of Daniel, which is 65 kilograms. So if we go through the motions in our calculator, we find that the velocity of Daniel in the x direction after the collision is, we'll say about we won't round this one as much. We'll say 5.68 meters per second. I'm not going to round this one as much because I want to put them together at the end. I need velocity in magnitude and direction. So this is my x setup. I'll do the same thing for my y. So P1y is equal to P2y. So I'll set this up exactly as I did with the x. So mass of Rebecca times V1r in the y plus mass of Daniel times V1 Daniel in the y is equal to mass of Rebecca times V2 of Rebecca in the y plus mass of Daniel times V2 of Daniel in the y. So again, this is a zero term because Daniel has no initial velocity. And I know that I will be able to find V2 of Daniel in the y direction because I know all of the other variables. So solving for V2 of Daniel in the y direction, I would have mass of Rebecca times V1r. Actually, we can make another simplification here. Because Rebecca's initial velocity is 0 in the y direction, at least as we've defined it. So that means that V2d is just going to be negative mass of Rebecca times V2 of Rebecca in the y direction over the mass of Daniel. So substituting here, I have negative 45 kilograms for the mass of Rebecca times the y velocity of Rebecca after the collision, which we found to be 6.4 meters per second, over the mass of Daniel, which is 65 kilograms. So V2 of Daniel in the y direction is going to be negative 4.43 meters per second. So here are my two components, and I will put these two together. So when I put these two together, I will say that the magnitude of my velocity is just going to be the square root of V2 Daniel x squared plus V2 Daniel y squared, all square rooted. So this magnitude will be the square root of 5.68 squared plus negative 4.43 squared. And so when I go into my calculator, I find the magnitude of this velocity to be 7.2, we'll round it, 7.2 meters per second. And the angle at which this is going, or the angle at which this velocity is pointed, is going to be the arctangent of the vertical component, so V2 dy, over the horizontal component, V2 dx. So that will be the arctangent of negative 4.43 over 5.68. So the angle at which this velocity is directed is a negative, we'll just say 38 degrees. So this right here is my answer to part A. So here's all of part A. I just did conservation of momentum in each direction, and then I put those together into a single vector with magnitude and direction. Now part B asks, what is the change in total kinetic energy of the two skaters as a result of the collision? So for this particular part, I'm going to say my change in kinetic energy is going to be, of course, K2 minus K1. So this will be 1/2 the mass of Rebecca times her final velocity, really I'm talking about final speed, squared, plus that for Daniel. So his final speed is again what I'm looking for. So this is my K2. Minus my initial kinetic energy, which is going to be the mass of Rebecca times her initial speed, plus the mass of Daniel times his initial speed, which we actually already know to be 0. So we'll say this term is 0 because Daniel has no initial speed, and we'll substitute in all of our values. So I have 1/2 45 kilograms times Rebecca's final speed of 8 meters per second squared, plus 1/2 times Daniel's mass, 65, times his final speed, which we just found to be 7.2. We'll go ahead and put this in brackets because it's a little complex, minus 1/2 put that in brackets as well, 1/2 times the mass of Rebecca, initially still 45, times her initial speed, which was 13 meters per second, square that, and then go to our calculator. So the change in kinetic energy of our entire system will be, oh, actually, don't forget this square, a change of negative 677.7, I won't round this for now, joules. And so that means we have lost some kinetic energy in the collision, which makes sense because human bodies tend to deform a little bit when they collide with things. Question 8.29 involves you riding a skateboard with no friction in a straight line at a speed of 4.5 meters per second. So let's do a quick sketch. So here is you on a skateboard, and you are moving at a speed of 4.5 meters, actually, hold on, let's call this V1, is equal to 4.5 meters per second. So I have a mass of 55 kilograms, and I'm riding a frictionless skateboard with a mass of 5 kilograms. So I'm going to say that my mass is, in fact, 60 kilograms. Now, a friend who is standing above me drops a sack of flour into my arms. So this is before I receive the flour. After I catch that flour, I'm going to continue moving, but all of a sudden my mass has changed. So now I have a sack of flour, which is just a thing. So all of a sudden my mass has changed. I have some change in velocity because all of a sudden I now have a mass of 62.5 kilograms that is moving. So now I need to say, oh, this is mass 2 and this is mass 1. Well, what's happening? We know that momentum should be conserved. So let's take a look at this. My momentum, so this is part A, my momentum initial will be equal to my momentum final. Now this is all in one direction, so I'm not going to worry about the fact that it's only in the x direction. So here, that would be m1 times v1 is equal to m2 times v2. So in order for me to have a new mass, I need to figure out what new velocity I'm going to have. So that would be m1 times v1 over mass 2. So substituting here, I would have an initial mass of 60 kilograms, an initial velocity of 4.5 meters per second, over a final mass of 62.5 kilograms. So now my new speed will be only 4.32 meters per second. Okay. So since the sack was dropped vertically, how does this actually affect my horizontal motion? So this is actually a really interesting question, right? Because typically we think in order for there to be an acceleration, so in order to have a change in velocity, I must have a force, right? So a change in velocity implies that there is an acceleration, which means that there had to be a force. Well, how does this end up working? When I drop the flour sack into my arms and I catch it, I actually have to do work. So I have to do work to accelerate the flour sack to my speed. It doesn't really matter which force we're talking about at this point. I still have to impart some of my energy to that flour sack in order to have it move with me. So when I do that work, that means that I must necessarily take that energy from somewhere. So I lose some energy to my flour sack in order to do that. It is just simply not a linear thing. So some of my kinetic energy goes to the sack. And since k is not linearly related to velocity, I can get this from my conservation of momentum. So it's kind of weird, but think about how energy has to go between our objects in this situation. Some of that energy has to go to the sack. And since the kinetic energy is not linearly related to velocity, I can do this through conservation of momentum. Now finally, C says I throw the extra weight into the air. What is the speed while the sack is in the air? Well, when I throw my sack up into the air, it should continue to move at the same speed with the same horizontal speed. Right? Because there is no force now in the horizontal direction on my sack. And so what that means is that I have no force on me. So the thing that's strange now is that sack, or the sack, is part of my system. Which means, since my momentum is conserved, that it's a constant. So now I'm talking about not only myself, where momentum must be conserved, but the momentum of the sack as well. So the sack that is now part of my system that I throw up, and I now have an internal force that I had to throw it up with. So my throw was an internal force now. Compared to before, where my force was technically external, right? There's something that came from outside of my system that I knew of that caused there to be a change in speed. So, this is kind of a weird situation, but it's worth thinking through. I advise you, if you have any further questions, to see me. Question 8.41 involves two vehicles colliding at an intersection. The yellow car, which we'll call just a car, has a mass of 950 kilograms. The truck that it collides with has a mass of 1,900 kilograms. So when they collide, they stick together. Now that tells us some information. This is an inelastic collision. So what does that tell us? That tells us that only momentum is conserved, not energy. So after the collision, the wreck slides at 16 meters per second in a direction 24 degrees east of north. So be careful how this is defined. So what I'm going to go ahead and say is we will be using conservation momentum. We will need to do it in 2 dimensions. So we will be splitting this up into an X and a Y system. So I'll go ahead and say that V final in the X direction will be equal to the speed times, let's say this is the X direction, times the sine of 24 degrees. So that's going to be 16 times 16 times the sine of 24 degrees, which is pretty much 6.5 meters per second. And in the Y direction, we will have V2 times the cosine of 24 degrees. So my V in the Y is in this direction, so that's adjacent to my angle. So that'll be 16 times the cosine of 24 degrees, which will be approximately 14.6 meters per second. So I am rounding this, so your answers may be different in the actual end. So now I'm going to go to my conservation momentum, and I know that I have to do this in 2 parts. So I have to do a Y and an X separately. So for the X direction, my initial and final momentum will be the same. And so I break this into a few parts. So before the accident, I had the car traveling at some speed in the X direction, and I had the truck, which was traveling at some speed in the X direction. And that will be equal to, so since this is an inelastic collision and they stick together, I can treat them as one mass after the collision. So it will be m car plus m truck times the final velocity of the two in the X direction. So I can put these together. Let's treat them as one object. So thankfully I can make a simplification as I go here. My truck is only traveling north. This means that its initial X velocity equals 0. Actually, we'll say this is V1 truck in the X direction is 0. For the car, the opposite is true. The car is traveling to the east, so its initial Y velocity is 0. So that helps us because we can actually get rid of this entire term in our equation. So if I want to find the initial x velocity of the car, I will have v1 c of x equals the sum of the two masses times their final speed over just the mass of the car. So v1c in the x direction will be 950 kilograms plus 1900 kilograms times their final speed in the x direction, which will be 6.5 meters per second, over the mass of the car, which is just 950 kilograms. So the speed of the car in the x direction will end up being 19.5 meters per second. So that is the only speed of the car, since the car is only moving in the easterly direction before the collision. So now we'll move on to the y direction. So P1y is equal to P2y. So setting this up, I have the mass of the car times V1 of the car in the y direction plus mass of the truck times V1 of the truck in the y direction is equal to the masses together times their final speed in the y direction. So again, we can make a simplification. The car's initial speed in the y direction is 0, so this term is 0. So that means if I want to find the truck's initial speed, I just have v1 of the truck in the y direction equal to mass of the car plus mass of the truck over mass of the truck this time times their final speed in the y direction. So my final speed of the truck will be the 950 kilograms of the car plus the 1900 for the truck over the 1900 of the truck times the final speed in the y direction, which is 14.6 meters per second. So the final speed of the truck in the y direction will be 21.9 meters per second. So these are our two speeds for the vehicles prior to the collision. And we can do this solely with our conservation of momentum because they are moving exclusively in a single direction. And since our collision is inelastic, we can only really rely on conservation of momentum. For question 8.43, you need to know what a ballistic pendulum is in order to actually solve this problem. So let's start with some sketches. Our before sketch will involve this 12-gram bullet colliding with our ballistic pendulum that is at rest. So what does this look like? I have a bullet. It's drawn not to scale, but it is a bullet. And it has a mass of, so we'll say this is mass B for bullet, of 12 grams, or we can say that's 0.012 kilograms. And it has an initial speed, so V1 of the bullet, of 380 meters per second. Then it collides with a ballistic pendulum. So it's a block of wood that is suspended from a cord. So here's my cord, and the length of this cord is 70 meters. So I'll just say L equals, I'm sorry, not 70 meters, 70 centimeters. So I'll say that is 0.7 meters in length. The mass of this block of wood, so we'll call this mass of the ballistic pendulum, so P, is 6 kilograms. What we want to know is, given these values for the bullet's initial speed and mass, how high will the pendulum, the ballistic pendulum, rise? So we know that it'll impart some amount of motion to the pendulum and it will rise some height h. So what are we going to do? For part A, we're going to start by realizing what type of collision this is. The bullet sticks in the pendulum. So bullet sticks in the wood. What does that mean? That means that this is an inelastic collision. So I only want to deal with momentum being conserved. So where I go from here is, I want to say, momentum 1 is equal to momentum 2. And I don't really care about the vector part this time because it's just in a straight line. Actually, I'll say that there is a velocity going this way. So my momentum will be the mass of the bullet times v1 of the bullet plus the mass of the pendulum times its initial velocity, which we can actually say is 0. It starts from rest. And that's equal to the bullet and the pendulum together plus their final speed. So this term is 0, as we just stated, and I want to find v2 because that is the only unknown in this equation. So I have mass of the bullet times v1 of the bullet over the total mass of the bullet and the pendulum. So this will be the mass of the bullet, 0.012 kilograms, times its initial speed of 380 meters per second, over the 0.012 plus 6 kilograms. So the speed of the bullet and the pendulum after the collision would be a fairly small 0.7585 meters per second. So I'm not going to round this one much because I'm in the middle of the problem. So once the bullet and pendulum are embedded together, then the bullet and pendulum move together. So now the bullet and the pendulum move together. Well, why is that important? From here, energy is conserved. So now we need to use conservation of mechanical energy. So we have our kinetic energy. Actually, let's write it as such. So we'll write our whole conservation of energy. So actually, let's say this is at point 2. So K2 plus UG2 plus UE2 plus work done by other forces is equal to K3 plus UG3 plus UE3. So for us, we have, I'll zoom in, we have no elastic energy either before or after. There's no work done by other forces. Initially, my block is at the lowest possible height, and finally, I have no kinetic energy once I reach my maximum altitude. So I have K2, which is going to be 1/2 mass of the bullet plus mass of the pendulum, times V2 squared is equal to, and UG3 will be mass of the bullet plus mass of the pendulum times G times H. So we're looking for H in this case. So solving for H, I would have, in fact, you see the masses canceling out. I have 1/2 V2 squared over G. So substitution here would give me V2, which we found to be 0.7585 squared over 2 times G, which we'll use 9.8 this time since we have an awkward number and need to use a calculator anyway. So the height that our pendulum goes to ends up being only 0.029 meters. So there is our answer to part A. Now B says find the initial kinetic energy of the bullet and the kinetic energy of the bullet and pendulum after the bullet collides with the wood. So for part B, our initial kinetic energy is going to be, so this is just KB for the bullet, so this is going to be 1/2 mass of the bullet times the velocity of the bullet initially, so V1B squared. So that's going to be 1/2 my 0.012 grams, or kilograms rather, times 380 meters per second squared. So plugging this into our calculator, the bullet speed ends up being 866.4 joules. And so now we can move on to part C. So part C says the kinetic energy of the, we'll say, bullet and pendulum combo. So that will be 1/2 the mass of the bullet and the pendulum together times just V2 squared, since they're moving as one. So that'd be 1/2 0.012 kilograms plus 6 kilograms times the 0.7585 meters per second squared. So the kinetic energy of the bullet and pendulum together immediately after the collision would be only 1.73 joules. So there's quite a large amount of kinetic energy lost in this case. For question 8.46, we have a 0.15 kilogram glider, so we'll just call it a block, with a mass of, we'll just say this is mass 1, how about that? Actually, let's call it mass A. It has a mass of 0.15 kilograms, and it's moving to the right with a speed of, so V1A, of 0.8 meters per second. It collides head-on with a collision, or with another glider that is moving in the opposite direction with a much higher speed. So we have a mass of glider B, which has 0.3 kilograms, and it's moving, so V1B, at a speed of negative, or velocity of negative 2.2 meters per second. We want to find the final velocity of each glider if the collision is elastic. So I'm looking for V2A and V2B. So since this is elastic, that tells us two things, right? That P is conserved and our energy is conserved. So let's set it up as such. So first off, from conservation momentum, I know P1 is equal to P2. So this would be mass of A times V1 of A plus mass of B times V1 of B is equal to mass A times its final velocity, so V2A, plus mass of B times its final velocity, V2B. So here, none of these are 0. I can only do this to that degree. So I'm actually going to go ahead and start plugging in values because I know that both V2B and V2A are unknown. So I'm going to need values in order to end up solving for anything at some point. I'll need a system of equations. So from here I can say 0.15 times 0.8 plus 0.3 times negative 2.2 is equal to 0.15 times V2A plus 0.3 times V2B. So on the left-hand side, put this in our calculator and we find that this side is negative 0.54, and that's equal to 0.15 V2A plus 0.3 V2B. Now we can clean this up a little bit by dividing everything by 0.15, and that actually makes this look a lot better. We end up with negative 3.6 equals V2A plus 2 V2B. So there is one equation that I can use. I'm going to go ahead and label this equation 1. Now, the next part comes from our conservation of energy. So my kinetic energy 1 plus UG1 plus UE1 plus work done by other forces equals K2 plus UG2 plus UE2. So we can already cross out elastic potential energies. There's no springs here. And we can also cross out gravitational potential energies because we stay at the same altitude the entire time. And then there's no work done by other forces that we can assume. So really I'm just conserving kinetic energy here. So I have 1/2 ma times v1a squared plus 1/2 times mb times v1b squared, let me zoom in here, is equal to 1/2 ma times v2a, so the second velocity of a, squared, plus 1/2 times mb times v2b squared. So simplification allows us to get rid of all of our halves, and we end up with a situation where we need to plug in values again. So I have, for mass A, 0.15 times v1a, which I've forgotten is positive 0.8 squared, plus mass B, which is 0.3, times v1b squared, which is negative 2.2 squared, equals 0.15 times v2a squared, plus 0.3 times v2b squared. So going through the calculator motions here, we find an equation that has a left side of 0.1, I'm sorry, not 0.1, 1.548 is equal to 0.15 V2A squared plus 0.3 V2B squared. So I'll go ahead and divide everything by 0.15 again to make this slightly better looking and get rid of some of these coefficients. So I have 10.32 is equal to V2A squared plus 2 V2B squared. So this is my second equation. And I now have two equations with two unknowns that I can use to solve for those unknowns right now. So putting these equations together, I'm going to start with equation 1, and I'm going to solve this for V2A because that's really easy to do. So from equation 1, I have V2A is equal to negative 3.6 minus 2 V2B. So I'm going to plug this into equation 2. And what I get is 10.32 equals negative 3.6 minus 2 V2B squared plus 2 V2B squared. So from here I need to expand my binomial that's squared, and I will get 3.6 times 3.6, which will be a positive 12.96. And then we have first and last will be, let's see, that'll be 2 times 3.6 plus 2 times 3.6. So that will be plus 14.4 V2B. And then finally we'll have plus 4 V2B squared. So that's plus 2 more V2B squared. And so collecting all of these terms and solving or setting it equal to 0, we would have 12.96 minus 10.32, which is a constant value of 2.64, plus 14.4 V2B plus 6 V2B squared. So at this point, we need to use some kind of quadratic solver. So solve the quadratic however you like. I'll go ahead and pause it here, and you can do it however you want. I'll give you a moment to find that. So I get x values of negative 2.2 and negative 0.2. So we have to figure out which of these two makes sense. So it doesn't make sense for block 1 to remain at the exact same speed. I guess I shouldn't say x, I should say v. So my two velocities. So this is one solution, but this is my other solution. So I'm going to reject the same value and say that my velocity is something new. So v2b I'm going to write as negative 0.2 meters per second. So that's to the left. Now I can go in to equation 1 and plug this in and solve for v2a. So v2a will be equal to negative 3.6 minus 2 times negative 0.2. So V2A in this case will be, so V2A appears to be negative 3.2 meters per second. So before we put an exclamation point on the end of this, let's make sure this makes sense. So we have a glider with twice the mass hitting a glider that is half as big, and it also seems to be moving like 4 times as fast in the leftward direction. So when we go through this, we see a weird situation where my smaller glider is actually pushed to the left and the big glider continues slightly to the left. So this seems to make a bit of sense, even though it is not extremely intuitive. Question 8.71 has the CP designation. This just means that it is a cumulative problem. So with this one, we will actually be doing not only collisions, but we also have some amount of projectile motion. And the reason I know that is if I sketch my table with a leg here, I have a block of wood sitting on the edge, and so I have a mass of this wood that is 8 kilograms, and it's sitting at the edge, which means that V1 wood is 0, and the table that it sits on is 2.2 meters above the floor. So I'm going to label this as H1. Then there is a blob of clay that slides along the table I'm assuming without friction, with some speed. So the mass of this clay is 0.5 kilograms, and the speed of the clay initially is 24 meters per second. So the combined object leaves the edge of the table and travels to the floor. What horizontal distance will it travel when it reaches the floor? Or will it have traveled? So this will make some kind of path off of here, and we want to know the distance that it goes. So we'll call this distance d, or actually we'll call it delta x. So to continue with this question, I know that it is split into two parts. There's a collision that occurs, and then there is a projectile motion that occurs. So for the collision, I know that this is an inelastic collision because the clay sticks to the block. Therefore, only P is conserved. So my momentum initial will be equal to my final momentum. So let's zoom in and do this. So I have the mass of my clay times its initial velocity plus the mass of my wood block times its initial velocity is equal to the combined mass of the clay and the wood block times their final velocity, which we'll just call velocity 2, or speed 2. So now I'm going to go ahead and simplify by saying the wood is not moving initially. So my second speed with which they move together will be mass of the clay times its initial speed over the mass of the clay and the mass of the wood together. So plugging in values for this, the mass of the clay is 0.5 times its initial speed of 24 meters per second over 0.5 plus the 8 kilograms of the wood. So the speed with which they start to move together ends up a fairly ugly 1.412, we'll say, meters per second. So this right here is equal to v naught in the x direction for our projectile motion. And we know that v naught in the y is equal to 0. So what does this mean for us? Well, from here, we can go into our projectile motion equations. So we have two pieces to the puzzle. We have the time that it's in the air, and we have the distance that it travels. So the time that it's in the air comes from the y direction motion. So I have a change in y, which is equal to v naught y times t plus 1/2 ay t squared. So I have 0 initial y velocity, so this term vanishes. And now I just have change in y is equal to 1/2 ay t squared. Well, ay is just g, so if I move this around solving for time, I have 2 times delta y over g square rooted. So for this particular instance, I have 2 times my change in height. Well, the table is 2.2 meters tall, so I'm going to change my height by negative 2.2. My acceleration is actually negative g, I should have written. So that's negative, I'm going to use 9.8, since I need to use a calculator anyway. So the time that my object is in the air, pretty much 0.67 seconds. Now I can use this to find my x direction. So in the x direction, I have v naught x times t plus 1/2 ax t squared. My x acceleration is 0, so this term is 0. So now the change in horizontal position is just going to be my v naught x, which I found from the first collision part to be 1.412 times the time that it was traveling through the air, which is 0.67 seconds. So the distance that it travels horizontally will be, we're not rounding this, 0.946, maybe we'll round it to that, and 0.946 meters is the distance that it travels. So again, this question is meant to reinforce the fact that collisions can occur in conjunction with other styles of motion that we have studied before. Question 8.78 is getting pretty close to what we would call an AP style question. I have a piece of putty that falls onto a frame from a height of 30 centimeters, and I want to find the maximum distance that the frame moves downward from its initial equilibrium position. So I'll go ahead and remark that the mass of the putty is equal to 0.2 kilograms. The mass of the frame is equal to 0.15 kilograms. Now the spring is initially stretched 0.04 meters. So let's say that this is, we'll call it y naught, which is negative 0.04 meters. Now why is that important? Well, this is a cumulative problem again, so in order to figure out the spring's spring constant, we can use this information. So I know that for the frame, so I'll go ahead and say this is the frame, I have a force of gravity pulling down and a spring force pulling up. And this is in equilibrium initially. So from application of Newton's second law in the y direction, my spring force minus mg will be equal to ma in the y, which is 0 for equilibrium. Well, this m that we're talking about is the mass of the frame. And my spring force is going to be negative kx, or actually we'll say k delta y, how about that, minus mg is equal to 0. And this is mf in this case. So my k will actually end up being mg divided by negative delta y. So my k should be, for the mass of the frame, 0.15 times 9.8 over negative of my negative 0.04 meters. So the spring constant here is going to be 36.75. And since everything is in base SI units, I know that's newtons per meter. So why do we need this spring constant? Well, when the putty hits the frame, it's going to begin stretching the spring. So what's going to happen? First off, I need to know the speed of the putty in the frame after they collide. So first off, I have an inelastic collision between the putty and the frame. So let's do that. Only momentum is conserved, so P1 is equal to P2, and really it's in the y direction since we're only moving in the y direction. So I have mass of the putty times V1 of the putty plus mass of the frame times V1 of the frame is equal to mass of the putty and the frame together times their final velocity. So, unfortunately, even though I know that the frame starts with an initial speed of 0, I don't actually know V1 of the putty. So how do I go about finding V1 of the putty? Whew! V1 of the putty is going to come from this falling distance. So I can actually find V1 of the putty from a conservation of energy situation. So to find V1 of the putty, I'm going to say K1 plus UG1 plus UE1 plus work other equals K2 plus UG2, 2 plus UE2. So initially it starts from rest. Finally it has some kinetic energy. Initially it starts with some height. No springs involved in this particular part, and no work done by other forces. And at the bottom, it has run out of kinetic energy. So I have mass of the putty times G times H equals 1/2 mass of the putty times V2 of the putty squared. So V2 of the putty is actually equal to V1 of the putty in this case, just using 1 and 2 as we've gotten to it. So this is actually H1, and now we're good. So mass of the putty we see cancels out, and we find that V2 of the putty is going to be the square root of 2GH1, which for this situation is just going to be the square root of 2 times 9.8 to be consistent, times H1, which is 30 centimeters or 0.3 meters, all square rooted. So V2 of the putty will end up being 2.425. And so that's meters per second. So now I can take this in as V1 in the second part. So this is the speed. I guess I'll go ahead and use a different color. So this is the speed of putty right before the collision. So we can take that and plug it in over here. So we're going to be looking for V2 because we want to know the speed that they start to move when the spring begins to stretch. So V2 is going to be mass of the putty times this V1 of the putty, that we're slightly misnomer here, over the total mass of the putty and the frame. So V2 is going to be the mass of the putty, which is 0.2 kilograms, times this velocity we just found, 2.425, over the 0.2 plus the 0.15. So the velocity that the putty and frame move together with will be approximately 1.386, I guess we'll round it to, meters per second. And so now we can transition into another conservation of energy. So this is, we'll use the other color here. So this is speed of putty and frame together. And so now we go into another conservation of energy situation. So we have K, actually at this point we'll call it K2, plus UG2 plus UE2 plus work done by other forces is equal to K3 plus UG3 plus UE3. So let's be careful here. Initially we have some kinetic energy that we're moving together with. Initially we have some height because our object is going to start at some height and then it's going to move downward. We're also going to initially have zero elastic potential energy. My spring is at equilibrium to begin with. Is that true? Not exactly. So this is actually non-zero in this case, right? We have some initial potential energy because even though I'm at equilibrium, I have some stretch to my spring. There is no work done by other forces. Once we get to the bottom, our kinetic energy goes to zero. We also have no more gravitational potential. We cannot go any further. And we have a maximum potential energy due to elastic deformation. So let's go ahead and put this together. So 1/2 the mass of the putty and the mass of the frame together times V2 squared plus my height is going to be the masses together, mass of the putty plus mass of the frame, times G, times what we'll say here is, we'll just call this one H. So we move down some distance H from our equilibrium. Plus 1/2 K times my Y naught squared is equal to a final 1/2 K times Y naught plus H squared. Woo! So, actually, let's go back and double check real quick. So H is some positive distance. So H is measured up from here. And so our stretch is just going to be whatever Y naught is plus H. So it's what we really want to think of here is Y naught plus H is like an absolute value. So just be careful there. So when I go through all of this, I'm going to start substituting values because I can't really get rid of anything. So I have 1/2 0.2 plus 0.15 times the 1.386 that I found for V2 plus 0.2 plus 0.15 times, let's go ahead and use 9.8 again, times some H. I don't know what that H is yet. Plus 1/2 our K, which we found to be 36.75, times our Y naught, which was negative 0.04 squared, equals 1/2 our 36.75 times, we'll just say 0.04 plus H squared. So it doesn't really matter if it's stretched or compressed. I need this to be a positive number. So what this ends up with is a nice big quadratic in terms of H. So I'll let you go through the algebra for that. I'll pause for a second and I'll do it myself, and then we'll write it out. All right, so working through this, we have from this term 0.33617, I'll leave it there, plus 3.4, let me write that better, plus 3.43h plus 0.024 is equal to 18.375 times the expansion of this binomial, which is going to be, so 0.04 times 0.04 is 0.0016 plus 0.08h plus h squared. So putting all of this together, we end up with a single quadratic equation in terms of h, which will have values of, on the right-hand side, negative, actually we'll do it this way. We'll say 18.375 h squared minus 1.96h, then minus 0.33617. So this is kind of a gross quadratic, but if you go through the trouble and you actually solve it, you find two values for h. Those values are negative 0.0915 and 0.196. All right, so the question is, which of these two is the correct one? So this is in meters. So the question is, which of these is most correct? Well, we know that it starts off with a displacement of only 0.04 meters in the negative direction. So it seems then that if we're looking for h's that solve this equation and give us the exact right value, we're probably going to want the smaller of the two. So for this particular problem, we're going to say that the actual h we want is, I believe, going to be the negative value. So I'm going to go with the negative value here, and the caveat is I may have made a mistake up here with the sign by not including the negative 0.04, but I believe this is actually going to be correct, because if we're going with the same sign consistency otherwise, this seems to be about the right size. So the one thing I will say is, even if these answers aren't exactly right, this might be where my error lies. But with such a long, convoluted problem, even if you can get this far, you're doing pretty well.